Stewart. It's good to be back here. And I noticed some familiar faces from when I was here last year. So for you guys, you'll be just hearing more data over again. There'll be some overlap between last time, but hopefully most of it will be. So let's see. So here's this character, Sherlock Holmes, who said, it's a capital mistake to theorize in 401 hat data. And Holmes, of course, is known as this sort of paragon of logical reasoning, being able to come up with deductions. But when you really look at it, he's not really doing logic. He's not really doing deduction. And if you pay attention to what he does and says, you realize that. So here he's talking about the way he comes up with his fabulous solutions and balancing probabilities to choose the most likely. And here he says he can't really say what an individual man is going to do. But in the aggregate, you can say with precision what an average number of people will do. So really what he's doing is he's collecting lots of data and doing probabilistic analysis. So Holmes is Bayesian and not a legit. Now nowadays, of course, we have even more data. And the question is, can we do amazing things like Sherlock Holmes? What can you do with all this data that's available? And certainly more people are going into this direction. So I looked at the papers from the Computational Linguistics Conference over a number of years that had words like statistics or probability or Bayesian and so on in the titles. And it went from 0% in 79 to 55% this year. And that was just looking at the titles. If I looked at the abstracts as well, I think I'd probably be up in maybe 75 to 80%. But another 30% or so, it was just so obvious that they're doing probabilistic stuff that they didn't bother putting it in the title. And that's a big change from where we were in the 80s and early 90s, when people were still thinking in this much more sort of logical tradition rather than data-driven probabilistic. So why the change? So one way to look at this is to say, well, there's two things you can do when you're trying to solve a task. One is to think really hard, come up with a better algorithm, and the other is to apply more data and see if you get better results anyways. And so this is a meta-study by Banco and Brill from Microsoft Research, and they looked at the task of word sense disambiguation. So you have a word that has two possible senses, and try to come up with the right answer. And they looked at 5 different algorithms. And it's not important what the algorithms were, but one was a support vector machine, one was a boosted decision tree, or whatever. And they noted that most of what you talk about in the journals and so on is along this axis. And people say, well, the first researcher did this good, and then the next guy did this good, but now I have this new algorithm that's all the way up here. And that proves that my approach is better than all the other approaches. But what Banco and Brill said is that there should be more room for improvement in this direction than in this direction. So rather than arguing about is this algorithm better than that algorithm, all you have to do is go out and get 10 times more training data. And now all of a sudden the very worst algorithm from down here is performing better than the best algorithm did when you had less data. And when you get 10 times more, it happens again. And eventually you have to asymptote out. And now when you get out to 1 billion words of training data, now it makes a little bit of difference. And you can start talking now about what algorithm makes sense. But notice the big jump from here all the way up to here just by adding more data. So look for the data first before you start worrying about the algorithm. Seems to be the conclusion. Now, of course, the reason you can do that is because more data is available. So I was an undergraduate at Brown, and it was very exciting there that they had 1 million words of text collected. And they were on these big 9-track tapes that were like this big, that run through their IBM mainframe, and they'd actually do stuff with it. And for a long time, we didn't get much past 1 million words. There were other collections, the canonical collections that people used. And it wasn't until the 90s that the Linguistic Data Consortium at Penn started going beyond about 1 million or so words. They had several collections that are 10 million or so. We just donated some statistics over 1 trillion words. We'll talk about that later. But of course, that's dwarfed by the internet, which is maybe 10 or 100 million words, depends on how much you want to count. And just, to some extent, the internet is infinite because you can always go on to another page. But most of it is not that useful once you get past 100 trillion words or so. So what we donated to the LDC is a corpus over 1 trillion words. So tokens means individual words one after another. Some of them the same word being repeated. So 1 trillion words, 95 billion sentences, 13 million unigrams, meaning distinct words. And this was a surprise to a lot of people. So this was all in English, no foreign languages, or we tried to read out the foreign languages. And people make estimates of, well, maybe there's 100,000 or so words in English. And then we came up with 13 million. So, of course, most of those are numbers and proper names of places and people and spelling errors and things like that. But it really confirms, and I don't have the chart here to show it, but Ken Church did this work in the around 1990 or so, where he followed news stories and said, the number of distinct words seems to be linear. It never slows down. And we've duplicated this here, going out a couple of orders of magnitude farther than here. Then bigrams is 2-word sequences, so 300 million of those. And then it's interesting that it sorts to asymptote out. So if you look at 3-word, 4-word, and 5-word sequences, it's all about the same. You don't actually start getting more than that because of the structure of the language. And here's just an example of the data. You can go ahead and order this data. It comes on 6 DVDs, about 25 gigabytes of data, and it just lists these sequences of words. And here's an excerpt from the foreground. And so it says, for these sequences that start with, serve as the word beginning with IN, independent seems to be the most popular one. That is counts. And so we look at what can you do with these models, and there's a progression on 2 fronts. So one is, in the early days of statistics, we looked at these small parametric models. So you did linear regression, where you had a bunch of data points and try to fit it with a line, and there's exactly 2 parameters, the slope and the intercept, and try to choose the best one. So then we moved to some semi-parametric models, like neural nets, where you have, instead of 2 or 3 parameters, you have hundreds of thousands or maybe tens of thousands. But now we're moving on to these non-parametric models, like nearest neighbors, where the number of parameters is essentially the number of data points. So the more data you have, the more you move down to this front. And then over here, a similar kind of thing, where you can start with a model like these, say, like the linear regression model, where you say, well, I've decided that this data is best fit by a line, and all that's left to do is figure out what the numeric values of those 2 numbers are. Or I've decided it's best fit by the Gaussian. You start from there where the analyst figures out the model and just fits the parameters, to a blank slate model where we say, well, we don't know anything about it. We'll just get it all from the data. We won't have any preconceived notions on what the structure is. Okay, so what can you do with the data? One thing is associations. So this is a classic thing in data mining. You have one thing, how is it related to another? And here's one example of it. This is one of the first things we did. I first got to Google in 2001. I was interested in this. First guy I hired was Simon Tong, who was a student. So Simon was a student of Daphne Kohler, who was a postdoc here, and he put together this demo based on some of the work that we did, and it was the first thing on the lab.google.com site. And the idea is that you can put in individual items and then see what comes back. So if you put in Pablo Picasso and Matisse, you get back this. And it's interesting that, it starts out with Impressionist paintings. Painting goes on and has other kinds of painters, but they're all sort of iconoclastic. And I think Ansel Adams is in there, so it's not 100% painters, but you can see the relation, and you can see as you go farther down, it's getting a little bit farther away from the center of this cluster. So that works pretty good. Here's another example. You put in cat and dog, and you get these things, and it's kind of a mix of most popular pets. And I think there's some influence from the Chinese astrology animals and fairy tale animals. And then it's interesting, you can do just a little change. It's just change one of those words. So it kind of goes. I don't know, that's what I wrote down. Well. Another thing you can do is this suggestion. So we had this suggest data. It's now integrated into the toolbar. So this is using a different source of data. So the first, when I took a previous, using co-occurrence statistics from words on the web. This is using our search history to say what are the really popular searches. If you start typing ARTIF, it thinks, well, artificial intelligence is the most common thing you could be searching for, but it might be the other AI. I went to Purdue once to give a talk and said I was talking about AI, and that's what they thought. Well, take there. And so, and this user data is the sort of second source of information that's very useful to us and fun to leverage. So we launched this Google Trends. You can see cycles here. So if you see moon, well, turns out it's exactly a 28-day cycle. And if you search for watermelon, it's high summer and summer. Not surprising. You search for World Series, it's this 1-year cycle. And those of us from Boston are proud that the Red Sox won. And the White Sox are just barely beating out the World Series of poker.
Question: what are the y-axis?
So this is volume of searches, but there are no numbers on it. So there was, we had a lot of privacy concerns when we launched this because we didn't want to give away individual people's search information. So we did a couple, and we know that there's all these theorems on how to derive data from databases by local searches. We didn't want people to be able to do that. So we did a couple things. One is we sample over a small portion of the data, and we sample over different portions for every query. We don't put any numbers up on the axis, and we leave out results if there is less than a minimum number of searches. 200 searches a week. If it's less than that, we figure it's sort of too unusual, too private to show it. And so we can't show the numbers there because we don't want you to be able to survive.
I'm so sorry, was there a consistency between full moon and actual number of searches? Was that what the previous chart was showing? That was kind of
interesting. So this is saying this is the volume of searches for full moon. It is high on these days as well. People want to know, is it full moon today or tomorrow or what day is it?
Okay, fascinating.
Other things that are also periodic here is American Idol versus Cinco de Mayo. And then you can also see where these topics are interested. So here's machine learning. The trend is pretty much flat, but you see all the interest is in Asia. Not over here, so. I also noticed the trend is going a little bit down, but I think from comparing to other terms, I think that doesn't represent anything about machine learning. I think what that represents is as Google grows, the percentage of people who are nerds becomes lower. So, too bad for us. You can sort of track trends and things. So here we're comparing 4 companies. Google in the blue, a growing company. MySpace in the red, a very hot company over the last year. Wikipedia, almost the same as MySpace. And Microsoft, a more mature company, flat across the board. But then when you go down, it's interesting. Again, you see a lot of this interest in India. Here is more European countries and Asian. And you can see that MySpace is pretty much uniquely a U.S. phenomenon, whereas the others are more global. Okay. Now, the next thing I want to address is extraction of facts from text and question answer. So you might have seen this. If you ask a natural language question, what's the population of Japan, or a sort of truncated question like population of Japan, then you see a result up at the top as well as seeing the regular search results. And so we've extracted out a bunch of facts and built a database that when we match query against that, will show that result. So how can you do that? Well, basically there's 3 approaches to it. One is you can write very specific patterns for a specific site. In some cases we've done that. So we know there's lots of good information in the CIA fact book. So you can say, well, take all the URLs that match this pattern, and then the country will be the thing that matches these parentheses inside this regular expression, and the population will be the thing inside this regular expression. So that's the database. Or you can do a general pattern that works across multiple sites. So you can just think about it and write down, well, I think a good pattern is you search for the population of this is that. And you can look for that on any site, so that's much more general. Or you can say, well, I don't even want to have to write this down because that's fine for population and capital, but if I want to do 100,000 different relations across 20 of the most popular languages, that's going to be a lot of work. So could I just learn the patterns from examples without having to do anything? And here's an experiment done by Marius Pasca that demonstrates how far we were able to get with that kind of thing. So what he did is he said, well, we're just going to start off with some facts. We're not going to write down any patterns. We're just going to give examples of the relation we want to pull out. And the relation in this case is just a tuple of 2 arguments. So Bob Dylan in 1941, Vincenzo Bellini in 1801. These are reported examples of the first-name relation. And then, so given those, you can just search for those in the corpus and see where they occur. And 1801 and Vincenzo Bellini occur in this sentence. From that sentence, you can say, well, let's just break it up. Let's just break it up into the parts that match the first argument, match the second argument, the part in between, the part before, and the part after. We can do that automatically because we have these 2 parts, the R1 and the R2. And then you get lots of examples of that. And now the trick is, can you massage those and come up with general patterns? In order to do that, you're going to have to learn things like the generalization of what a month is and what a country or a location in which you could be born and things like that. Marius was able to do this, and his goal was to learn 1 million facts. He started with a small sample of only 100 million web pages, and achieved 90% accuracy, a much higher accuracy if we were willing to do less than 1 million facts. These are the 4 most productive patterns, and this is just the infix part of the previous rule. Of word C4 followed by born followed by in, where C4 class that was learned by the generalizer to be this set of words, is was. So is born in, was born in, etc. The second one was born on, and then this OO stands for a 2-digit number, a day of the month, and then C3 is this class. And I had to learn all those individually. Didn't know ahead of time what the names of the months were, what the abbreviations were. It learned them by clustering together similar kinds of patterns, and then so on. There's a comma, B period, and then a month and a date, and so on. And these all came out automatically from just applying over the data, and it turns out there's about 7,000 of these patterns we needed to get those events. And here's the precision results. So he didn't look at all 1 million of them to grade them, but he just chose 100 or so from different ranges within the facts. They're sort of ordered by certainty. And so of the first 10,000 most certain facts, 98.5% were correct, and then as you get down towards the end, it falls off to 75%, and overall it's 90-something. Okay. Then the next example I want to talk about is statistical machine translation task, taking text to one language and producing it in another. And again, this is an approach that traditionally has been taken by this kind of logical approach. You go out, you hire a bunch of linguists, they write dictionaries, they write grammar rules, you run it, you debug it, you scratch your head, and you keep on keeping that cycle. So we decided to do that without any of the linguists. So we built this system, and we were able to achieve the best results in the competition for translation between Arabic and Chinese to and from English. And we did that without anybody on the team who spoke any Arabic or any Chinese. Now, we did have German speakers and French speakers, and we were debugging the system. We worked in that language first, so there's definitely some sort of linguistic intuition there. But for the final product, they're out of the loop. So how do you do statistical machine translation? Well, the first thing you do is you collect parallel text in 2 languages. And when I was in Berlin this summer, I did that in my hotel room. So here was the German text, here's the corresponding English text, here's another example. You collect a bunch of those. The next thing you do is you line them. So you take 2 of the texts and say, how do the words match up with each other? And here I've given the correct map. But of course, at the beginning, I don't know that. I know, the word Kunst in German could refer to any one of the words here, or it could refer to several of the words here. So you start out, you just have a probability distribution. Or maybe you can have a prior that says it's more likely that the lines are kind of up and down rather than crossing, but it's a kind of a broad prior. You need lots of examples to get that right. And then you just solve this equation. So the E hat is the English translation, the best English translation of the foreign text, and it works out to be the maximum overall possible E's of this estimate of the probability of E, that's how good is E as an English sentence, times the probability of F given, that is, how good is E as a translation.
Do you do this on words or on bigrams or?
So we'll see. So it's, you have to do it on more than words. But first I'll just show you how well it works. So here's some text in Arabic, and here's the results. And I try to underline the places where there's kind of disfluencies, but it never really gets the wrong word or leaves words out. It's more like it's leaving out, there should be an article or something like that. It's a little bit disfluent. Tell it wasn't a native speaker. But people have done tests of reading comprehension on things like this. You do just as well with this as you do with a fluent English. For Chinese, not quite as good. I think there's a larger difference between Chinese English than between Arabic and English. So here, it's more like 2 or 3 disfluencies per sentence rather than 1 per sentence.
Could you elaborate slightly on how it differentiates between ideograms and actual sort of parsed text or parsed alphabets? I mean, that's a hard thing to kind of grasp. I guess.
Yeah, so we'll get to it. Okay. Yeah, if we don't, ask me again. Okay. So here's a sentence in Chinese. Don't ask me what it means. And so we go to our statistics and say, we did that word alignment. We have this big corpus of possible translations. What are the translations just looking at that first character? And here are some of the possibilities. And then you look at the next character, and then you get that. And then you say, well, let's look at the two together. And you look those up. And you get some compositional. So his was in this column, and letter was in this column, so that's just a composition. But you get other things that are completely different. So this can also, as well as being two common words, it can also be a name, and optionally with or without the honorific there. That's just the way the language works. And then you keep going, and for these three words, you look at your corpus and you say, oh, well, I realized that there was this example where these three words together meant vaccine also. So that's sort of more specific than looking at them individually, and there's more evidence that maybe that's the right translation. And you go through like that, and you get subsequences of words come up with these possible translations. And you go through all the way through the end, and you have this kind of lattice of possibilities. Now you multiply all the probabilities together, and you come up with possible sentences, and they each have a number associated with them, and among them there's some pretty good ones, and among the ones that are not so common. And so basically that's all there is to it, and the rest is just kind of tricks. One of the problems with the tricks is you can't exhaustively consider all the possibilities of every combination of subsequences, so you have to search for them. And essentially, to make this practical rather than just theoretical, you need these three components. So there's this translation model, which is the estimate of this probability of the form given the English. And that we get from this bilingual parallel corpus. And we use about 20 billion words for that. Then there's the language model of target language. So taken forward, we want to generate not just a sentence of English that's a possible translation, but also one that's a good sentence of English in its own right. And that you can obtain from a monolingual corpus, which of course is a lot easier to get. It's easier to get a lot of English than it is to get examples of English and Chinese that are the same article written the same way. And so we can use trillion words for that. And then you need a decoding algorithm that, given the new sentence, finds the translation that maximizes that and do research to find the best one. So a little bit more on the word alignment. I showed the example before of how they line up. So one way to do it is you can just go through and say, take all the words here in German and English and write a table of all the possibilities, and when you get to the end, just count them up. And so here we say house. Well, the ones with the biggest counts are house and is and the, so those are all possibilities. But note that is and the also have other possibilities that are much higher, so that makes them less likely. We can work out the math. We'll have to work that out. But if you only did one word at a time, you wouldn't get very far. And so the next step is to do phrases. Now, if we were a linguist, the first thing we do is say, well, we've got to have noun phrases and verb phrases and reduced relative clauses and all this complex stuff. So that seems to be hard to do. So we'll just skip that. And we'll define a phrase as being a consecutive sequence of words. And that makes things a lot easier. You've lost some of this linguistic knowledge, but I think you've gained something as well, because when you try to squeeze the linguistic knowledge into the rules you can write down, you make some mistakes there. The linguists aren't perfect. So they miss something that they aren't able to capture the right generalizations and the right exceptions to the generalizations. We miss something because all we have is sequences of words. We don't know anything about this tree-like structure. But it works out in the end that at least for what we're doing, we don't miss what we need. So we look at sequences of words. Here we're looking at two-word pairs. We can go up more than that. Currently we can go up to 7 words. And we see how those align with each other. So we have this table of translations. It's not just one word, but it's up to sequences of 7 words translating into another sequence of 7 words. So the phrases capture this local reordering, and that's important. So one of there's a couple problems with just doing a word at a time. One is it's really hard to represent idioms. Kick the bucket or something. Doesn't really have anything to do with the translation of the bucket. The other thing is when you have languages with different word order, so in English usually it's subject, verb, object. Other languages have a different order. If you're doing it word by word, you got to pay the probabilistic penalty to move each one of those words one by one from the beginning to the end of the sentence. And if it works out right, you're willing to pay that penalty. But in the phrase-based approach, you can pay that penalty just once and say, I'm going to move this whole phrase once. Pay that one penalty for moving it, and now I'm done. That helps a lot. So all in all, it's a much better approach than the single-word approach. And the only disadvantage is you need a huge storage space. Now, I've gone over, I have these 20 billion words of parallel text, and I've got to store all subsequences to about 7 of them. That's a lot of space. But fortunately, that's something that's become feasible now that wasn't before. So, in the past, people have been looking at 3-word sequences and training on maybe 1 billion words. We've been able to push it up to 7-word sequences, training on 1 trillion words. And the training, I say training as if it was some complex learning algorithm. It's basically counting. And then you have to do a little bit of smoothing before the zeros show up. Okay, so we want to solve that formula. And you go ahead and you try to solve that. You come up with the best translation. Then you start playing around with it for a minute. And you notice that if I raise this to the 1.5 power, I get a better result. And so then you go back and say, well, geez, there's something wrong with my theory. Is the definition of probability wrong? No, I don't think so. It just means that the relative error in these two models. Is there a question?
Yeah. I'm just curious, do you have a sense of how many words an individual human brain is exposed to before it becomes a competent bilingual translator?
No. Work that out. Right, so back to this. So just doing the straight multiplication doesn't work quite right. This works better. And then you can say, well, in general, maybe I should have lots of exponents. And so then we move to a model where we say, well, instead of just having 2 exponents, let's take this log linear model where we have the sum of the product, depending on if you're in the log space or the original space, of these features, h sub m, times the parameters that you learn. And the idea is you learn the right lambdas to minimize the error. So the whole thing looks like that. There's lots of features up here. You're searching for the best answer, and you get the output out. And the features all have to do with these subsequences of words. And we tried all these things. We tried parse trees and part-of-speech tags. We had one of the best part-of-speech taggers written by Thorsten Branson, our company. We tried getting that to work. We tried throwing in WordNet, tree bank, and so on. And none of those things helped. So all the stuff that they're representing was already represented in the words, or at least represented to the degree that we can make use of it. And more data seems to help. So here, remember I said there was 2 sets of training data. This is for the bilingual. This is for the monolingual. This was last year's where we only had 200 billion. We've gone beyond that this year. And it seems like it's still linear. We haven't gotten to the point where our apps is cutting out. So we expect to keep on doing better as we add more data. You skip this. And you look at the result of the field in general, the best system increasing linearly. And you talk a little bit about some of the tricks. So you have to store these trillion or so probabilities, and you really don't want to waste space. So if I have to store them as a double, I will, but if I can store them as a single or less, that would be nice. So you just start experiment. You represent it with a different number of bits and see how well the system does. And turns out you only need 4 bits. That was something we didn't really expect. And I think it goes back to the kinds of things that Feigenbaum was saying 20 years ago, where he was saying, I don't believe this probability stuff. You don't need all those numbers. Well, he's mostly right. You only need about 4 bits numbers. So the precision isn't that important. But having the numbers is.
Which slide are you putting off that means 4 bits?
Right. So I'm saying you represent this is the probabilities for the word co-occurrence. You represent them as 4 bits. You do as well as if you had more. And then if you raise quite a bit with 4 and 3 and 2, and then really bad. Then another trick is this word alignment takes a lot of memory because we have to do all these different words. And remember I said there were 13 billion words. What if I could do less words? And so one way to do that people have done in the past is stemming, where you cut off the endings, the EDs and the INGs. Of course, that's hard to do because you got to figure out what the endings are. So what if you said, well, we'll just truncate the words to a certain number of letters. Forget about letters. So again, we're taking sort of the simple approach rather than the complex linguistic approach. And do that and figure what's the best place to truncate. So started out saying, let's truncate to 10, 9, 8, 7, 6 characters, and it seems like it doesn't make that much difference. We do pretty well at truncating all the way down to 6 characters. So that worked pretty good. Let's keep going. And the surprising thing is, when you truncate to 5, you actually do a tiny bit better. Everything. And it also happens at 4. And then when you go down to 3, it's back to baseline, and when you go down to 2, you do worse. So we said, well, okay, we don't know why it works, but we'll represent it with 4 characters. So there's some trade-off of generalization there. I'm not sure exactly how it's working, but that seems to be the right answer. As an engineering coach, and a linguistics coach, we don't worry about it too much. We like to figure it out. We just go ahead and say 4 characters. And here's the result for the 2005 NIST competition. There was a 2006 competition that I can say that we think we did very well, but the official results are embargoed for another couple of weeks. So they have 2 tracks, what they call the large data track, we call the small data track, and what they call the unlimited data track, where you use your own resources. But here, not many people competed with it, so it's not that interesting. But we did pretty well here with a pretty good lead over the other guys.
What does it mean?
Very interesting question. So this is called the Blue Score. I forget what the acronym is, but basically the problem is, if you really want to know how good your translation was, you take your translation, you give it to an expert translator and say, give me a score from 1 to 10 on how well I did. But that's not very good for automated systems that want to be able to do a lot of turnaround and training quickly. So they came up with an automated approach that doesn't need a human expert in the loop. The way they do that is they have a fixed corpus of test sets. And then for those test sets, they go out and they hire 3 translators, and each of them comes up with their translation. And now that's done offline. Now the online part is you have your recorded translation, and we just compare that to each of the 3 possibilities that have been logged and sort of measure the overlap. And so this measurement is not a precise measurement, because if you came up with a beautiful translation that was very creative and different from those 3 other guys, you get a bad score. But it turns out that this measure correlates very well with the more expensive measure of actually handing it off to an expert having the score. So the field accepts this, non-perfect score because it's easier to work with.
0.5 is good.
Right. So 0.5 is good. Humans are about 0.6. Right? So humans only agree with themselves 2/3 of the time. Right? And so that's actually a problem for the whole field, because we're getting up to the point where we're close to where the measure can no longer distinguish. We'll need to measure. Okay. So in summary, our goal here was to improve the state of the art. look at machine translation not as a problem in linguistics, but as a problem in decision theory, saying, given the data, what's the right action to take? We did very well in these evaluations in 2005, 2006. Here it says we got the best results. I don't know if I'm allowed to. We think that's good. And we think that the answer is you need data, you need statistics, you need engineering to figure out how many bits to do and things like that, and you need a lot of computers. And in the future, we expect to continue doing better because the graphs are all linear and we haven't started out. And we got a couple minutes for questions.
I hate to start out with an apology, but I'll start out with two. First of all, to my colleague Stuart Russell, professor of computer science here at Berkeley, whose name I absolutely blanked on at the beginning of this meeting. Stuart, my profound apology. And secondly, I'm not sure whether the remote campuses heard a single word of that, but we had some mic trouble at the beginning, so if they didn't, they're not hearing this apology either. So we'll move on to questions. We have 10 minutes or so. Please.
Is there any type of language you've ever tried that didn't work, like maybe a Hopi language or some obscure cultural language format that you just didn't anticipate?
Well, we thought Arabic and Chinese were kind of obscure, right? So we did them for two reasons. One is that that's the language that NIST chose for their competition, and they did it for sort of obvious reasons. In fact, it was Russian that was big, now Arabic and Chinese are big. So.
I thought as a way to test the outer fringe of the audience capacity.
But part of the problem is that for these very fringe languages, there's not enough training tests. So if we tried it and didn't do well, we wouldn't know if there was something else that we didn't have enough tests.
I don't do machine translation, but I heard from my colleagues that the main difference between Google's algorithm and everyone else's was just that they had more machines and more data. Is that true, or did you do some of those tricks before the competition with the exponents of translation?
So the question was, what's the difference between Google and the other people in the competition? Is it just that Google had more data and more machines? Well, it couldn't be just the more data because some of the tracks there was everybody got exactly the same data. Google still did that there. So I think having more machines is a very important part of it because it allows us to turn around and experiment much faster than everyone else. So it's not the online performance of actually doing the search that matters, but it's, gee, I have an idea, I think we should change this. And if I can run that idea and get an answer in 2 hours, I'm going to take advantage over somebody in another group who takes 2 days to get that answer. So I think that definitely helps. And I think it also helps that we took this engineering approach and said, well, we're willing to consider anything. And I think some of the other groups feel like a little bit like, well, their group is trying to push this one direction or that one direction. We didn't feel like we had to do that. We didn't have to uphold some approach. We just took whatever worked.
So I have a question. So suppose the original translation is not correct. That is possible. How do you solve there is some small mistake in the translation or some sample text?
Right. And of course, there's going to be lots of errors, right? Because if we've got these billions of words of text, there's going to be plenty of places in there where there are spelling errors and mistranslations and all sorts of errors. And we just hope that there's enough good stuff to outweigh the bad. But if there's not, then we're going to replicate that mistake. Right? So we've got this, we're going out to 7 grams. So, there's another approach. I talked about the sort of linguistic-based approach and the statistical-based approach. There's another approach that used to be considered separate, which is example-based translation, where you say, let's just look up what somebody did in the past. And we sort of incorporated that into the statistical probabilistic model because we have examples up to 7 words long. And so if there's an example of that, we won't always retrieve it based on the surrounding context, but we'll be sort of encouraged to retrieve things that we've seen before. And if we saw them and they were wrong, we'll just duplicate that error.
I just wondered if you have a way of distinguishing when you're learning the corpus between when something has just a less likely, a less frequent translation, and when something's just a mistake? So do you just throw out things that have low probability and then you lose that translation? Or?
So we keep all the data, but I think you're right that things that are low probability will have a tendency not to show up. And so even if there was, because remember there's two parts to the model, right? So, and you can make two kinds of errors. You can have an ungrammatical result, or you can have an error in translation. We tend to recover from these ungrammatical results. If there was an example of translation that was ungrammatical, then we retrieve it. But then you have to pass that through the monolingual model, and it would say, wait a minute, there's something wrong with the sentence out here that you retrieve it from your database. It's not very grammatical. So there is some correction there.
Back for a moment to the question of the computing resources that we use to facilitate your approach here, which is very, very convincing and very exciting. Would you comment on roughly how many resources are we talking about? Is this something that Google and maybe the U.S. government could afford and nobody else? Or, I mean, is it a prohibitive amount of resources required?
Depends on how much you want to spend, right? So,
Yeah, well.
So you probably want to be in the hundreds to thousands of computers. So that's in the $100,000s to $1 million. A couple $1 million. Is that a lot or a little?
Yeah.
Yeah.
Where do you go about getting a 20 billion word bilingual corpus? I mean, is there some automated process involved in that, or is this all just?
So the combination, the community as a whole has collected several of these types of texts, and the other ones we just go out on the web and find. And you can do that by a number of ways. A lot of them we do by URL patterns. So things like newspapers, they'll have two URLs that are the same, except one has a /en/ and the other has a /cn/. And you just look at those and say, well, we're going to assume that these are translations. Parliamentary proceedings is another good example. So in the European Union, all the long, boring reports have to be translated into all the languages.
This is like good things come in small packages. So how do we actually recognize these good things rather than the small probability and don't destroy them? And because you gave an example of you can come up with a very good innovative way of presenting something, but since it's not seen too many times, you're going to throw it away. So is there any way to find these things?
So you're saying something that only shows up once or twice, but that's very good?
Right.
Yeah. So I guess if it only shows up a few times, but it's so much more precise than everything else that it covers the data better, then we would tend to find it. If there's other things that cover the data equally well, but just aren't as fluent or whatever, then all bets are off. We wouldn't see that. And, I guess if you said, well, I want to build a system that will recover that, I always say you got to put some human in the loop to do that. So maybe we can have something where we allow our users to comment on the quality of the translation, say is the sentence good, is the sentence bad, and we start getting feedback. Then we have this check. But lacking that feedback, all we can do is treat everything the same. And maybe we could say, learn that some sites or some translators are better than others. So we have to try to do that.
You mentioned that the linguistic categories, noun phrases, verb phrases, and all that, there's mistakes made, there's miss some things that by taking the statistical approach you don't miss. But can you use the statistical approach to feed back to linguistic theory to say what the categories should be to identify missing categories?
Yeah, so I don't think it's so much that there are categories that are missing. I think it's just that there are so many exceptions, and the rules we can write don't allow us to represent that. And so most of the formalisms say you can write out this rule, but you can't say very easily when it doesn't apply. And so I think if we have the right formalisms, we can do that. Another thing is what are you going to conditionalize? So if you're just, the test you're looking at these things says, if you're just looking at the categories, the noun phrase or whatever, then you're going to miss a lot. And so the parsing and generating systems that do better tend to be the lexicalized programmers that say, this is a noun phrase, but it's a noun phrase whose head noun is dog, cat. So you take that head noun and you pass it up the tree, and it's a complex category that says, noun phrase, dog. And then maybe it has some other features as well. And I think if we knew more about how to represent all of those features and conditionalize on that, then we could get some demand. But we don't have grammars yet that will do that. And, it seems clear to me that there's information there that's useful. And a lot of people in the field are trying to do it. In fact, our guy, Franz Ock, who's leading our group, has a bet that's been going on for a few years with Kevin Knight of the ISI group, one of the other top groups in the field, called the syntax bet. Kevin's group is pushing hard to try to put syntax in. And for 3 years now, Franz has got to win a t-shirt that says, I won the syntax bet. And the t-shirt's starting to get a little bit old and frayed around the edges, but he keeps winning. And some year, he's got to lose, right? There's got to be at some point. Somebody will figure out a way, maybe it'll be Kevin, maybe it'll be Austin, maybe it'll be somebody else, to say, here's a way to incorporate syntax knowledge that's helpful, but we haven't figured out how to do it yet.
One more question.
So you mentioned the features which didn't help. Could you also tell us some features which help in addition to the prior probability and the conditional probability?
So all the features are based on sequences of words. So consecutive sequences of words, and then other things like how long is the whole sentence, and so on. And but they're based on the identity of the words and the words next to them. And that's all we did. Combining them in various ways.
Great. I think if you have a few minutes, if there's any other questions, you can come down front. But with that, thank you very much, Peter.